So having understood what is dimensional analysis, what are dimensions, and what's dimensional formula, we'll try to understand here uses of dimensional analysis. The first use is what is known as the principle of homogeneity. And this very simple concept says that if we have an equation which relates a couple of physical quantities, the dimensions on the left hand side have to be same as the dimensions on the right hand side. For example, if Q is equal to W plus U, that means heat energy given is equal to work done plus internal energy, then the dimensions of Q should be same as dimensions of W and U, because only then we can add them. If W and U have different dimensions, if they have different units, we can't add them. We can't add length and mass, and therefore any equation should be in such a way that the dimensions on the right hand side and the left hand side are same. Similarly, these two add up and give you one physical quantities, and that should have the same dimensions as Q. In this case, the example that I have taken, this has the dimensions of energy, work also has the dimensions of energy, and internal energy also has the dimensions of energy. And therefore, this equation is valid. If the dimensions are not same, then the equation is not valid. And therefore, we can use dimensional analysis to check the correctness of an equation. Say, for example, you have an equation like S is equal to ut plus half at square. So you can find out the dimensions of all these three quantities, three terms, 1, 2, and 3, and check whether they are same or not. If they're same, the equation is valid, otherwise the equation is not. As you can see over here on the left hand side, you have length. So here the dimension is L1, m raised to 0, L raised to 0, t raised to 0 rather. This is u into t. So velocity is L t raised to minus 1 into t, so which is t raised to 1. So t raised to 1, t raised to minus 1 gone, so you'll be left with L, and that will be again m0, L1, t0, t0. Therefore, the dimensions are same. Let's confirm with the final term. Half is a pure number, so it will not have any dimensions. Acceleration is L t raised to minus 2, and then we have t square. So again, you have L raised to 1, m raised to 0, t raised to 0. Thus, we have confirmed that all these three terms have the same dimensions, and therefore, this equation is valid. So this is one use of dimensional analysis, that we can check the correctness of an equation. The other use of dimensional analysis is to establish relationship among various physical quantities. Say, for example, we know that the time period of a pendulum depends upon mass of the pendulum, length of the pendulum, and acceleration due to gravity. Supposing experiments help us understand that time period is dependent upon these three physical quantities. Then I can get an equation like T is equal to some constant K into m raised to the power A, L raised to the power B, and G raised to the power C. And now I can use the concept of dimensional analysis over here. So what I'll do is I'll find out the dimensions on both the sides. So on the left hand side I have time, so the dimensions over here are m0, L0, and t raised to the power 1. Let us look at the right hand side over here. K is a constant m, so this will be m raised to the power A. Of course L0 and T0, but I'm not writing that over here right now. Length raised to the power B, so L raised to the power B, m0 and again T0 over here, which I'm not writing over here. G is acceleration due to gravity, so it is acceleration, so L t raised to minus 2 for G, whole raised to the power C, because acceleration is length per time square. So if I simplify this, I'll get m raised to A, L raised to B plus C, because you have got L raised to C over here, and then I have t raised to minus 2C. This is equal to m raised to 0, L raised to 0, and t raised to 1. So by comparing the units, I have got this equation. Now, since this is true, the powers of mass on both sides should be equal, the powers of length on both sides should be equal, and the powers of t on both sides should be equal. Therefore, I can write, if I compare powers of mass, I get a equal to 0. So I have obtained the value of a. Now comparing the powers of length, I get 0 is equal to b plus c. And therefore I can write down b is equal to minus. Thirdly, comparing power of time, I'll get 1 equal to minus 2c. And therefore I'll get c equal to minus half. Putting this value of c of minus half over here, I'll get b is equal to minus of minus half. That will be plus half. So I have got the value of a, I have got the value of b, and I have got the value of c. And I can go back again to this equation and write down t is equal to k mass. A is 0, so 0. Length raised to the power b, that is half, and g raised to the power c, and c is minus half, minus half. Therefore, p will be equal to some constant k. M raised to 0 is 1, so that will vanish. So I'll get L raised to half divided by g raised to half. And we know that anything raised to half is square root, so I can write this equation as t is equal to k square root of L by g. And we can very clearly see that this equation is something which we have studied earlier. We know that t is equal to 2 pi square root of L by g, time period of a simple pendulum. And therefore, the value of this k is 2 pi. Of course, dimensional analysis doesn't give us this value. This value will be obtained by experiments. But but the dimensional analysis helps us get this equation. T is some constant k into square root of L by g. And it clearly helped us understand that time period does not depend upon mass, because here we got the power as 0, which clearly indicates that m vanishes from the equation, and therefore time does not depend upon the time period of a pendulum does not depend upon mass of the bob. So this is one more use of dimensional analysis. Dimensional analysis has certain limitations, and I'm sure while we did this, you would have noticed them. The first thing is, for the first limitation of this method is that the value of any dimensionless constant involved in the formula cannot be calculated. For example, here we were not able to find out the value of k. That was a dimensionless constant, and it doesn't help us. It just tells us that yes, there will be some constant. The value of that constant cannot be obtained. Secondly, we can use this for three physical quantities, or quantities which depends upon m, L, and t. So that was the second thing, m, L, and t. And we were able to, but if it depends upon more than one, more than three, then we will not be able to use dimensional analysis. And the last limitation of dimensional analysis is that by this method, the equation which contains trigonometrical ratios like sine theta, cos theta, and logarithmic terms cannot be analyzed. But in spite of all these limitations, dimensional analysis is a very, very important tool which we can use to understand the relationship between physical quantities and their units. Thank you.